Hello everyone, welcome to the class once again. I hope you're all doing good and you're the best of your health. In today's class, we'll be talking about gases, zeroth law, and many more things. So first of all, I told you about the ideal gases in the last class, that was in the last chapter, that they do not exert any forces on the neighboring molecules. We'll go ahead and we'll again use this concept to understand some laws of thermodynamics, and we'll start with understanding the concept of thermal equilibrium. Let's go ahead. First of all, let's understand what is thermal equilibrium. Now, in thermal equilibrium, as the name says, equilibrium, thermal equilibrium, that means temperature will be somewhere involved. Suppose if I take a body, let's understand the concept of thermal equilibrium. Let us say we have taken a body A. Now, if I take another body B. Now, suppose if I bring both the bodies in contact with each other such that they are in touch with each other and they can interact with each other. Let's say this is A again, and I'm making B to be in contact with A. Now, suppose initially, let's say the temperatures are different. So what will happen? Let's say A's temperature is higher than B's temperature. So what will happen? Heat will be transferred from A to B. That means A's temperature will start decreasing and B's temperature will start increasing. So what we are starting with, temperature of A, let's say it's TA, temperature of B, let's say it's TB. Initially what we have TA is greater than TB. As they are brought in contact, we can understand that heat energy will be transmitted. We all know that heat energy always flows from high temperature to low temperature bodies. So what will happen? Temperature of A will start decreasing as it is higher than temperature of B, and temperature of B will start increasing. This is what we will observe. And this change in temperature, and let's say this transmission of heat, will take place till the time both the body reach to a temperature when their temperature will be equal, and then when there will be no exchange of heat. So we'll say that a state of thermal equilibrium is attained. So what will happen at one point of time, if this is A and we have this as B, now after attaining the thermal equilibrium, let's say temperature of A is T dash A, temperature of B is T dash B, there will be no exchange of heat further. Therefore, temperature of A will be equal to temperature of B. That is T dash A will be equal to T dash B, both will be equal. So what we are finding in thermal equilibrium, that means both the bodies are going to attain the same temperature and there will be no exchange of heat between A and B. Such a state, or let's say such a point, will be said to be thermal equilibrium that is existing between A and B. Now, how to use this concept in understanding the zeroth law of thermodynamics? So let's go ahead and let's understand the first important part of the chapter, that is zeroth law of thermodynamics. I believe that thermal equilibrium is not too tough for you all to understand, and it's an easy concept. And again, one more easy concept that we are going to study, that is the zeroth law. And don't worry about why it is said to be zeroth law, because it's a very basic law and not too tough to understand. Zeroth law of thermodynamics. New chapter, interesting chapter, and let me tell you, it's a very easy chapter. Students find difficult in coming concepts within this chapter, but okay, we'll try to make it easy, and let me assure you that I will try to make every concept involved in this chapter to be very easy and easy to understand and simple to apply. Let's go ahead with zeroth law of thermodynamics. Suppose I take three bodies and they are connected in a fashion as shown. Suppose if I take three bodies as shown here, here I am keeping a body, let's say C. And let's say the C, and here I have a diathermic wall. What is a diathermic wall? That means heat can be transmitted through this wall. So let's say this is a diathermic wall. Diathermic, as it means, as it states that heat can be transmitted through this wall. The diathermic wall we have maintained here. Now we have taken two more bodies, A and B, separated through an adiabatic wall. What we have done, we have taken two more bodies. This is A, and let us take body B in the downward section, denoting with dot. Let's say we have taken body B here. A and B are separated through adiabatic wall, Let me show this. This is an adiabatic wall. If you are unaware about the term adiabatic, just take that through an adiabatic wall there can be no exchange of heat energy. There can be no transfer of heat energy through an adiabatic wall. So we got this adiabatic wall. A and B are separated through adiabatic wall, and here we have taken C. So let me represent C with this representation. Here we have C. Now you try to understand what will happen with C. A and B are going to exchange heat energy. So understand, with time A will be in thermal equilibrium with C, B will be also in thermal equilibrium with C. Now see, after some time this will happen. Initially temperature of each of the body is different, but as A and C and B and C are separated through a diathermic wall, they are going to exchange heat energy. So what will happen? A state will be reached when A will be in thermal equilibrium with C. So I am marking here A will be in thermal equilibrium with C, and similarly B will be also in thermal equilibrium with C. This is what we will be observing in this A and C and B and C cases. Now, zeroth law of thermodynamics says that if one body is in thermal equilibrium with second and another body is also in thermal equilibrium with second, so the first and third body will be also in thermal equilibrium. That is, as per this example, if A is in thermal equilibrium with C, B is also in thermal equilibrium with C, so it automatically implies that A will be in thermal equilibrium with B. This is the concept of, or let's say this is the statement of zeroth law of thermodynamics. So you can see here once again, A is in thermal equilibrium with C, B is in thermal equilibrium with C. Now, how to prove it? If we remove this adiabatic wall and if we put a diathermic wall between A and B, we'll find that there is no exchange of heat between A and B. This signifies that A and B has reached to a point of thermal equilibrium between them. So that actually signifies the zeroth law of thermodynamics. So what you will write, what your statement that you are going to use for zeroth law of thermodynamics, you can write in this one: if a body is in thermal equilibrium with another body, if a body is in thermal equilibrium with another body. Thermal equilibrium, I'm writing equilibrium in short, EQLB, that stands for equilibrium. If a body is in thermal equilibrium with another body, let's say if a body A is in thermal equilibrium with another body C, and this body C is in thermal equilibrium with body B, and this body C is in thermal equilibrium with body B, is in thermal equilibrium with body B. So zeroth law says that A and B will be also in thermal equilibrium with each other, and if this body C is in thermal equilibrium with body B, then A will be in thermal equilibrium with B. So it's very easy even for us to understand, and need not to go into the deep proof of this, because we can automatically understand that if A is not exchanging heat with C and simultaneously B is also not exchanging heat with C, that means both have reached the same temperature state. It's quite obvious for us to take that A will also be in the same temperature with B and they are not going to exchange heat energy. And that is the statement of zeroth law of thermodynamics. Then A will be in thermal equilibrium with B. Hope that it's simple and easy for us to understand this part. Zeroth law, not too tough to understand, a very basic law of nature. You can understand the same thing at your home also. If you take one body at a temperature and if you take another body, if you join them, you'll find that both will reach to a thermal equilibrium state. And you see that if one of the body is in thermal equilibrium with another third body, and the second body is also in thermal equilibrium with the third body, we'll find that automatically these two bodies are in thermal equilibrium with each other. Now, quite easy zeroth law of thermodynamics not too tough for us to understand. And if you've understood the concept of thermal equilibrium, you can easily make out the zeroth law of thermodynamics. So as this is simple, we'll try to make another concepts in this chapter to be far simple and easy to understand. Now, before going into the deep and depth of the chapter, let us have some knowledge of some basic definitions that will be used in this chapter. So I will detail you about some basic concepts that we will be using in this chapter. Basic definitions. Let's start with first one, thermodynamic system. First of all, regularly we'll be using this term in this chapter, thermodynamic system. Now, any part which has got a volume, anything which has got a volume to occupy and which has got temperature, pressure and volume, so that thing will be said to be a thermodynamic system. Any thing which is occupying, which occupies thermodynamic system, anything which occupies a volume, is can be said to be thermodynamic system. Oh, I wrote with white and then I'm writing with yellow. Please do take, I'm writing with yellow. Can be said to be a thermodynamic system. Can be said to be a thermodynamic system. Now, what kind of system in this chapter will be taking to be a thermodynamic system? Now, so you may be thinking that solid occupies some volume. Is that a thermodynamic system? Yes, that's a thermodynamic system. Liquid that occupies some volume. Is that a thermodynamic system? Yes, that is also a thermodynamic system. But let me tell you, in our chapter, in our this concept that we're going to study, we'll be taking gas enclosed in a container, and this gas is actually in such a condition that it is free, it can be made to expand, it can made to do some work. Such kind of system, that is such kind of gaseous system which is actually enclosed in a container, is taken to be a thermodynamic system. So what we'll be taking in this chapter, what thing basically will be referring to a thermodynamic system, we'll be having a container. There in the container we'll be having a piston which will be free to move, as I have shown you here. There's a piston, it is free to move. Now what we can see, we will be seeing that there will be gas that will be present in this container. Now we know that gas occupy the volume of the container. Now what we will be finding in this chapter, sometimes you will be finding that piston, by some external force, you will be trying to push the piston into the container. Through some external force, you can push the piston into the container so that the volume of the gas decreases. Sometimes you will be finding that through some source, we will make the gas to expand, and what we will be finding that the piston will be made to move out. Sometimes we will be finding that piston will be made to move out. If the gas expands, then we will be finding that piston is going to move in the forward direction. And sometimes we can apply force through some source. We can apply force so that the gas that is within the container, that is going to compress. So I'm talking about gas. Remember, I'm talking about gas. Now, what gas should have? It will be having some pressure. It will be occupying some volume. It will be kept at some temperature. These terms that I'm using, these are known as the thermodynamic variable. So let us go with the next term, that next definition that we should know, that is the thermodynamic variable. So our thermodynamic system in this chapter will be a gas enclosed in a system. Now remember one more thing, I'm not limiting ourselves to only a particular kind of gas, let's say oxygen, helium, hydrogen, any gas. You may take any other gas, let's say ammonia gas, you can take it in the system. Any gas, remember. And remember, gases, we all know that all the gases, if I talk about ideal gases, they will behave in such a way that PV equals to nRT will be maintained at a proper temperature. And we're talking about the ideal condition. The next thing, the second definition that we shall know, that is the thermodynamic variable. As I told you, if gas is kept in a container, so that means it is going to have some pressure, some volume, and it will be kept at a certain temperature. So thermodynamic variable. Now to denote the state of a gas, we require some basic variables, and these are pressure, volume and temperature. So let me mark down pressure, volume and temperature. All these are thermodynamic variable. Pressure, volume and temperature are thermodynamic variables, the basic thermodynamic variables. Now you may be thinking some more variables that can be used to denote the thermodynamic variables. I will talk about that, are thermodynamic variables. Now two more variables I am going to keep it here, that is the entropy. Need not to worry about the term entropy, we will be discussing it, and internal energy of a gas. Even these two are the thermodynamic variables of a gas. So let me point out, so we have entropy denoted with letter S, entropy, and internal energy, which will be using letter U to denote the internal energy. We will be talking about internal energy, don't worry about it. And internal energy U of a gas can be also taken to be the thermodynamic variable of the system. Entropy and internal energy of gas can be also taken to be thermodynamic variable. Can be taken to be thermodynamic variable, quite simple and easy. And we'll be talking about it, entropy also, need not to worry about it. Thermodynamic variable. Internal energy you can easily make out that we are talking about the internal energy content of a gas, and entropy, that is the randomness in the gas. More detail will be understanding this term later on, both the terms. Next thing, so we talk about thermodynamic variable. I believe that you are remembering about the ideal gas equation. Now this ideal gas equation lets us to understand if we have any two variables, we can easily find out the third variable. That is, if we are aware about what is the pressure, what is the volume occupied by the gas, we can easily tell what is the temperature of the gas. That is, if you know any two variables, third variable can be automatically reached on. So third thing that we should know, that is the equation of a state, and that is actually the ideal gas equation, which will be useful in determining the relation between variables and how to know any variable when you're aware about any two variables. Third one, equation of a state. Now equation of a state, we know that any equation which identifies the relation between pressure, volume and temperature, that is the equation of state. Now I am also using a term state. That means at what state gas is present. If in a particular state, if we know the pressure, volume and temperature, so we can say that the gas in such a state that pressure is this, volume is this and temperature is this. Now if you vary any one or two, we will be finding that the third can automatically be computed by using the ideal gas equation. Equation of a state on knowing any two thermodynamic variables, we can easily find out or compute the third thermodynamic variable on knowing any two thermodynamic variable. We can easily go ahead and compute and find out the third variable on knowing any two thermodynamic variable. The third can be easily estimated. And remember, when I talk about the three variables, I'm talking about the pressure, volume and temperature. Those are the basic thermodynamic variables. The third can be estimated using ideal gas equation. Remember, we are not talking about real gases. Real gases may behave in a different way. Using ideal gas equation. Now, what is an ideal gas equation? Hope that you would be aware about it. And that's quite simple. That is PV is equal to nRT. I believe that you are remembering about this ideal gas equation. Very simple to identify. If the number of moles will be fixed, the gas constant R is fixed. If pressure and volume, if you are aware about the pressure and volume, easily you can compute the temperature. Now, if you are aware about volume and temperature, again you can calculate the pressure. If you are aware about pressure and temperature, you can calculate the volume. If we know any two, we can easily compute the third one. That is the wonderful thing about this ideal gas equation. And it will be used many a times in this chapter. Many times we'll be using to prove certain things. So do remember this one. Now let me also tell you about this this gas constant, this R. In SI units, it's 8.314 joule per mole per Kelvin. This is the value of gas constant R. Remember what we tell this R? R is very simple. It is gas constant. Gas constant R is 8.314 joule per mole per Kelvin. Now, the same thing can be expressed in terms of calorie. It can be also be equal to 2 calorie per mole per Kelvin. It is approximately equal to, actually it's somewhat 1.98, but we will taking to be equal to 2 calorie per mole per Kelvin. That is the value of gas constant in terms of when the unit is expressed, energy unit is expressed in terms of calorie, and rest of thing, number of moles will be expressed in moles and temperature in Kelvin. So this was all about some basic definitions that we shall know. Now, one more thing I'll be taking about in this basic definitions, but before that, you have to remember the most required thing, the most three ones. First of all, thermodynamic system. Any gas enclosed in a container will be thermodynamic system, and we'll be seeing a piston will be there. It will be movable. Sometimes it will be pushed forward. Sometimes it will be brought back to compress the gases. Second thing, we were talking about the thermodynamic variables. We saw that pressure, volume, temperature are the basic thermodynamic variables to identify the state of the gas. I also told you about the entropy and internal energy of the gas. Even this can be also taken to be the thermodynamic variables of the gases. Need not to worry about the entropy and internal energy. That is not coming in our any equation right now, but we shall know about the pressure, volume and temperature. Third thing, equation of a state. I told you, if you know any two, you can easily estimate the third one. And the relation between these three is actually the equation of a state, that you are going to identify what is the pressure, volume and temperature, how they are related at any given point of time. The next one is quite important, which we will be using in this chapter. That is the thermodynamic process. The fourth one, most important one, thermodynamic process. Now I told you about thermodynamic system. Now a system can be changed. A system can be made to change its state variables. Remember, when I talk about state variables, I'm talking about the pressure, temperature and volume. So let me talk about thermodynamic process. First of all, we'll be talking about the process number A, that is the isothermal process. Isothermal process. What is an isothermal process? Isothermal. You must be knowing that thermal stands for temperature. So if the temperature is kept constant and if pressure and volume are made to change, such a process is known as isothermal process. So in this process, what we are going to keep? We are going to keep the temperature as constant. So if temperature is kept constant, and pressure and volume of the thermodynamic system is varied, if temperature is kept constant, and pressure and volume are varied, that is, you are changing the state of the system by varying the pressure and volume. Temperature is kept constant and pressure and volume are varied, that is, you are taking through a process, you are changing the pressure and volume. Pressure and volume are varied. Such a process is isothermal process. Such a process is isothermal process. Isothermal process. Now I'm talking about changing the thermodynamics variable of the thermodynamic system. Let's take the in diagram, let's try to understand what kind of process we are talking about and what is an isothermal process. Now remember, in Boyle's law, temperature was kept constant. So Boyle's law will be agreed in this isothermal process. Suppose if I take one state of the gas, let's say this is the case. This is a piston, that's gas enclosed within this container. Let me show you the gas that is enclosed within this container. This is how the gas I am showing you here, not too difficult for us to make out. Now suppose if temperature at this situation is 300 Kelvin, let's say, and through any means by lowering the pressure of the gas, we made to expand the volume of the gas. Let's say the gas is expanding. So what we'll be finding that the piston is going to move up. The piston is going to move up and gas is going to expand. This is what we will be finding. In this case, you see here, temperature has to be the same, that is 300 Kelvin. So I'm keeping for this also temperature to be 300 Kelvin. Only change is what is happening. Pressure was made to be lowered. Pressure was lowered. We found that volume started increasing. Hence, but still temperature was constant in this case. So this process from moving from this state to this state, this is known as the isothermal process. Process means what? Understand the concept process. That means you are changing the state of the system. And while changing the state, you will be changing the thermodynamic variables. And during some particular restrictions, if we restrict to some particular thing, so we will be naming such processes. In this case, we restricted temperature to be constant, so hence this process was said to be the isothermal process. Next one we have, that is the isobaric process. Next one we have, that is isobaric process. Now I believe that you will be making out with the diagram what kind of process we are talking about. Next one is isobaric process. Bars, you see the term bar. Bar stands for the unit of pressure. So that means iso, that means constant. Isobaric, that means we are talking about pressure to be kept constant. If during any thermodynamic process, pressure is kept constant, if during any thermodynamic process pressure is kept constant, such a process is isobaric process. Pressure is kept constant, such a process is isobaric process. So such a process is isobaric process. Now again we can understand here also the same thing, that pressure you have to keep constant, temperature and volume can be varied. Now see that we know that if temperature is going to be increased keeping pressure constant, we know that from Charles' law, we know that in Charles' law I told you pressure is kept constant, and if temperature is increased then volume is also going to increase because volume is directly proportional to temperature. Here I am going to keep, let's say pressure is kept constant and pressure is, let's say 1 atmosphere, that's okay. Let's keep to be atmospheric pressure 1 atmosphere. If this is the state, now if we vary temperature, we increase the temperature, so volume is going to increase, keeping pressure constant. So pressure here also, that is 1 atmosphere. So such a process will be termed to be isobaric process. Such a process will be termed to be isobaric process. Not too tough for us to understand since we are keeping pressure to be constant. pressure is constant, that means the process will be isobaric. And the same thing you can understand from the Charles law, in which pressure was kept constant and volume was to be directly proportional to temperature. That is what we have seen in Charles law. So this was all about the two processes, isothermal, isobaric. The next one, we have isochoric process. So let's go ahead with the third one, that is the isochoric process. Now isochoric, we kept, once we kept temperature constant, once we kept pressure constant. What about if we keep volume constant? And the same thing can be recalled by Gay-Lussac's law or pressure law. We have seen that volume was kept constant. Here, in any thermodynamic process, if volume is kept constant and rest of the thermodynamic variables are varied, such a process will be termed to be isobaric process. In any thermodynamic process, if volume is kept constant, remember, if volume is kept constant and rest of the thermodynamic variables are varied, volume is kept constant and rest thermodynamic variables are varied, rest of thermodynamic variables are varied, such a process is isochoric process. Rest of the thermodynamic variables are varied. Hope that you are getting each of the process very easily. It's quite easy to understand. And once again, if you watch this video, after watching this video, if you made your notes, if you just go through your notes, you'll be easily recalling each of the process. Rest of thermodynamic variables are varied. Such a process is isochoric process. So we are talking about such a process is isochoric process. Let's go ahead with this definition which we have taken down. Is isochoric process. Remember, in isochoric process, volume is to be kept constant. So if we go with the change in the thermodynamic variables, this diagram, volume is to be kept constant. So first of all, I'm restricting myself to, let's say, volume is 100 cubic centimeter, let's say. No change in volume, that means we have to keep the piston at the same position. So what I'm going to do, I'm going to keep the piston at the same position in this case. In this, whenever the thermodynamic variables are varied, so we have to keep the volume to be constant. You may just observe this. Volume is kept constant. This is what we have seen. Again, volume is to be kept constant and pressure and temperature is to be varied. I believe that you are remembering pressure is directly proportional to temperature, and that is what we have seen in the last chapter. We have seen in Gay-Lussac's law, pressure law, and this process is isochoric process. Isochoric process, that is when volume is made to be constant. Vary pressure and temperature, and we know that pressure is directly proportional to temperature. So increase the temperature, pressure will be increased automatically. You will be observing that as you increase the temperature, for higher value of temperature, higher value of pressure will be recorded for this thermodynamic system. And there's a change in the pressure thermodynamic variables. So such a change, you see, when you're going from one state to another state, understand. So we say that the thermodynamic process has taken place. Thermodynamic process has been taken place. This is what we mean by thermodynamic process. Three processes. Now, there are some more basic processes that we should know. Next one is, again, this will be a bit different from what we have learned till now. The fourth one is, that is the dth part, that is adiabatic process. As I use adiabatic term, just before I have used the term adiabatic, and I told you there is no exchange of heat through the adiabatic wall. So from there you can make out what is an adiabatic process. During a thermodynamic process, if there is no exchange of heat with the system and the surrounding, or any kind of heat is not exchanged from the system, that is, heat is neither given by the system to the surrounding, neither heat enters the system from the surrounding, such a process is adiabatic process. So what we can write? We can write that during any thermodynamic process, if no heat is exchanged between system and surrounding, such a process is adiabatic process. If no heat is exchanged between system and surrounding, no heat is exchanged between system and surrounding, such a process will be termed as adiabatic process. Between system and surrounding, such a process is adiabatic process. Such a process is adiabatic. Remember adiabatic. Remember this term, no exchange of heat, that is delta Q is 0. Such a process is adiabatic process. Hope that you have taken down all the 4 kind of process that we should know. If any more kind of process these are some standard process. There can be processes in which pressure, volume, temperature may change. So we are not limiting ourselves only to isothermal, isobaric, isochoric process. There can be certain process in which heat is given to the system, even pressure, volume, temperature is changing. Again, neither it's isobaric, neither isochoric, neither isothermal, neither adiabatic. So, but that is also a normal process. These are some standard process that we are actually adopting. We are letting the thermodynamic system to move through this process. So this, the fourth one that we have studied, that is the adiabatic process. In this, there is no exchange of heat. And in short, what we can write? No exchange of heat. So delta Q is 0. So either gas is going to expand, it's going to do work based due to its own internal energy, or if you do work on the gas, that means you are going to increase its internal energy. There will be no heat lost from the system. So if I try to show you the adiabatic process, let me tell you, if we start with this, and this gas, without providing any heat energy, it expands. It expands and it reaches to this state. Let's say we find that it expands. But remember, we should not let any heat exchange. So what I'm going to do, I'm going to put a adiabatic wall on all the corners of the side walls of the container in which the gas is kept. So this is, we can find that there's an adiabatic wall from all sides, so there will be no exchange of heat, and we can say that the adiabatic process has taken place. So if the gas expands, it will do work on the piston based due to its own internal energy. Let me show you. This is how the gas has expanded here. Simple, easy, and need not to worry about all these processes, and we'll be talking, I am using the term work done. I will tell you what is the work done in each of the process that just now we have understood. Last but not the least, that is the cyclic process. Quite easy one. Last but not the least, that is the cyclic process. Now, in a cyclic process, what will happen? See, in each of the process, we are varying the thermodynamic variables. In each of the process, we are varying the thermodynamic variables. If we know the initial variable, if we vary the variables and if we reach onto a final state, and again from final state we reach onto the initial state such that the initial variables, thermodynamic variables, are equal to the final thermodynamic variables, such a process is cyclic process. So if the initial thermodynamic variable are same as if the initial thermodynamic variables are same as final variables are same as final, such a process is cyclic process. Such a process is cyclic process. What do we mean by initial variable and final variable? That means if you know the initial volume, temperature and pressure, and if you take the processes through various states, but you bring the process in such a way that the final variables are same as initial one, that is the pressure, volume, temperature are maintained to be the same. That is, if I show you here, if pressure, volume, temperature are given in this case, you change the system through any way, but finally you have to bring it to the same state. That is what I'm going to do. I'm going to show you the final state that has to be same as initial one, and there can be exchange of heat also through the process, need not to worry about it. Final state has to be same, that is pressure, volume, temperature will be same as initial one. So this is, if I write pressure, volume, temperature as Pi, Vi, Ti, and here pressure, volume, temperature as Pf, Vf, Tf. So let me tell you, in this cyclic process, the initial value of thermodynamic variables and final value of each of the variables will be same. That is, initial pressure will be equal to final pressure, initial volume will be equal to final volume, initial temperature will be equal to final temperature. So such a process that we have gone through, that is a cyclic process. So I believe that today's class would be very much useful for you all to understand the basic part of the thermodynamics section that we are studying in this chapter. We studied about thermal equilibrium, we talked about the zeroth law of thermodynamics, we studied some basic definition. The most important one are the processes, the isothermal, isobaric, isochoric, adiabatic and cyclic process. The next class will be talking about the internal energy of gas and some more concepts. Till the time, you just revise and start practicing problems on the last chapter, and this chapter is very interesting and easy. I'll try to make it simple for you all to understand. Till the time, do take good care of yourself, and thank you everyone for joining me here.